So in this subsection, I want to talk about the sorting algorithm in Python's library. And it's called list sort because it's part of the list objects, but it's probably used on a little more widely scale. Let me lose a few words about Python first, just to make the statements that will come up a bit more precise. If you talk about Python itself, that's just a specification. It's a long document telling you how a certain programming language of this name is supposed to behave. But this is not really something you can run. It's just a document telling you how it should run. Then to complement that, because that wouldn't be much use, the Python Foundation maintains a reference implementation. So it's their implementation where they say, wherever the specification might be not clear or leave some leeway or so on, here's a reference implementation that should clarify this up and also shows you that it is possible to implement it in a reasonable way. And this is called CPython because it's written in C. So by and large, if you run Python on a computer where it was installed, it is usually CPython, unless you specifically do something else. There are some other implementations of Python, especially PyPy is another interesting one. And there's a few more which are not very well known. And most of them, apart from these two, are not as generic in that they don't support all the libraries that make Python so great. I think a large part of why Python is so popular is that it has really, really good libraries, and usually open source ones for all sorts of things. The language itself might or might not be your favorite. It's maybe not mine, but it has really good libraries. Part of the Python language specification, really, it's a built-in function, is the sort function on a list or the sorted built-in. You probably know the difference, but just in case, if you have a list and say .sort, then the list is modified. Remember, a list is a mutable object, so you can change the value, and sort sorts the list, which is often what you want because it means you don't necessarily spend extra space. There's also the sorted function where you pass a list as a parameter, and then it returns a copy of the list which is sorted. That's the difference. So when you need a copy, sorted is more convenient. Sort is usually more efficient. Because these are part of the language, they're implemented in C. And the algorithm that list sort uses is called Timsort, named after the inventor Tim Peters. And is exactly 20 years ago, I think now. Yeah, it's you can think of it as a way of merge sort with some twists to it. And I'll show you a bit of these twists, some of these twists on the next slide, but I will leave out many other twists. And now, since last September, at least in the alpha version of CPython, it actually uses our Powersort instead of some parts of Timsort. So I was really excited to learn this. It took, in a sense, 3 years to get from that paper into some production code. And here's a little comment just from, well, yeah, Tim Peters himself put the code together in the end and decided after he got very interested in playing with this and experimenting with different options, and at the end settled for this one. I thought you appreciate knowing this. So Python 3.11 is still in alpha, so you wouldn't really run it now unless you install unstable development releases. But it will probably be released at some point. I think it's in the 5th alpha or so. It probably goes through some beta. Can only be a few more years. All right, so this is my attempt to show the other end of the spectrum. We've talked about the very simple algorithms like merge sort, quick sort, like you have them in textbooks. And this is the other end of the spectrum. That's what's running in a concrete library and one of the most widely used ones. I guess the slide is a little scary, so I should have probably hidden this part first. In essence, Timsort is a weird way to do merge sort left to right. It's neither top down nor bottom up. It's a third way which is distinctively different, but has some benefits. It works by maintaining a stack of runs. And so it nicely fits into this topic with runs. And so it always works by finding the next run from the current position. So it extends, finds the next run and puts that on top of the stack. Now, so far it sounds a little similar to bottom-up merge sort, but remember in bottom-up merge sort we used a queue and we always paired up things as they arrived in the same order, and always pairs all the way back. And this didn't really work so well, which is something that Tim Peters realized. So instead, he uses a different way. So he puts the runs on the stack. So the topmost is the most recent that you just discovered. And then there's a set of rules that tells you what to do. And I think these rules are still somewhat magic, that they work at all. We'll see that they don't always work that great indeed, but that's something that was just discovered a few years ago. And yeah, in Tim Peters' own words, these rules were the first thing he discovered that didn't obviously suck. So he stuck with them. But they're indeed not the most thoughtful part of Timsort. So just to briefly explain how these rules work, they only ever look at the 4 topmost elements in the run stack. And they only look at the length of these runs. So if this says z greater x, it means the topmost run is longer than this third one. And if that's the case, it happens to be a good thing to merge the second and third. Why? Again, maybe not completely clear at this stage. There's a few other rules, so you always check them one by one. If A doesn't apply, if this is not the case, then you try this one. If that applies, you do this merge. If not, you go on. And you need all these 4 rules. What they intuitively try to achieve is that the runs on the stack are exponentially decreasing in length. The topmost should be the smallest, and then they always grow by a constant factor, roughly. But that alone is not quite good enough. People like this for various reasons, but one of the reasons why it's good, first of all, it picks up existing runs as the other methods. And secondly, it has good locality of reference in the sense that you usually merge small runs often, and you usually merge those early when they arrive on the stack, which is just after they've been discovered. So these elements are still fresh in your cache. And then you merge them quite a few times before you move on. That's one of the things that, that Timsort does well, and maybe slightly better than other methods. I should point out that this is the core of the algorithm to the extent that I need you to see it to make sense of the rest. There's many other parts. Maybe I can just mention a few things. If you find that the next run is really, really small, you actually don't stop there, but you extend it to some minimum size. And that is done with some binary insertion algorithm, because that happens to be more efficient if you have very small lists. Another thing is that when you merge runs, this doesn't do the standard merge all the time. It sometimes does what's called a galloping merge, where you sometimes save comparisons if the input is again structured in a certain way. And a few other tricks of this type. But they're not as relevant, and they haven't changed last September. It's just this part that we'll look at now. But the core version is as given here. You find the next run, put it on the stack, apply certain rules to maybe merge some parts, and then move on to the next run detection. And let me show you a case where the rules in Timsort don't work really great. They still work okay-ish, but not great. That's this input where you notice the runs have all length 1, 2, or 3. And there's a peculiar pattern in the run lengths, which means that our lower bound from before, this h, is roughly 316. And if you run peak sort on this, it gets close to that. But Timsort does what you see here. And I want to highlight that there's a few specific merges that seem just not very smart. And somehow you can, with this input, repeatedly trigger Timsort to do this not so smart move. And the not so smart move is, for example, here, you merge a fairly long run with a single element into just one bigger run. So you pay this whole cost of reading the long run again just to make the run one longer. That sounds like what you don't want to do if you minimize merge cost. And there's ways to do it. So I didn't put the tree for peaksort on it, but it just doesn't do this. There's no need to do it. And yeah, the example gets more extreme if you increase the input size. Asymptotically, Timsort does 50% more merge cost than necessary. All right. So while these merge rules are really not that great, the rest of Timsort is really nice and people like it. So we would like to keep this left to right structure in merge sort with a run stack. But we would like to replace these weird 4 rules with something more principled. And that's what we did with Powersort. The structure is still roughly the same. What has changed is we always look at the topmost 2 runs in one go. Otherwise, it's similar. You walk through the list, detect a new run, put them on the stack, and merge some things. Let me walk you through the example. And I will leave out one key part, which is the computation here of the power of 2 runs. Yep. And how the power is computed, you will see on the next slide. On the bottom here, you see the resulting tree, how it merges things up at the end. And I put this here so that you can keep track of what's going, whereas what's really happening is shown up here. So this is the current state of the array. It has certain runs. Again, the algorithm doesn't see those yet. It has to find them one after the other. And there will be a run stack popping up here. And I'll tell you how to compute powers on the next slide. We start by finding the first 2 runs, not just one. And we compute a magic number, the power of those 2 runs, or rather, the power of the split between those 2 runs. And in this case, happens to be 3. More on that on the next slide. And now you keep a stack of runs, where you also store the power. And the rule for the stack of runs is it's fine if the stack increases in power. And if not, you have to merge. So that's what that says here. If the new power that you computed is smaller than the topmost on the stack, you have to merge the topmost 2 elements of the stack. Here, we only have a single run, so there can't be a violation. So let's move on to the next one. For those 2, the magic number turns out to be 2. So we put this on the stack, but this is a violation because 2 is smaller than 3. So we have to merge those 2, these 2, which happen to be these 2, and we replace them with their result with the merge of A and B. And you see it inherits the smaller of the powers. That's how we can get back to the invariant. Okay? In the next step, we find these 2 runs, and their power is 1. So a similar thing happens. We put this on the stack, but it's a violation, so we immediately have to merge. And then we get these 3. Now let me point out when we merged before. So what we merge here is this node. Right? We merge those 2 runs. And similarly here, when we merge, that's this run, this node in the merge tree. OK, then we move on to the next stack. So here, the run invariant is maintained. There's only one run. So we go to the next one. the magic number is 2, so we put it on the stack, and this times is fine. It's going up if you move up the stack. And one more time. And then we are at the end of the array, so we go into this last part where we just merge top down the topmost two until we only have one run. And so this first merge again is this node. Then we merge the next two, which is this node. And finally, we merge the last two, which is the root. Okay. So if you paid attention, we did this one first, then this one, then this one, then this one, then this one. But it's a little easy to lose the order in the animation. Is it clear how this works if you have these blue numbers magically given? You just put the next run on the stack, and if that new run has a smaller power, you merge the topmost. And once that's no longer happening, you move to the next run. The key thing now is how you compute these powers. And that's a little mysterious if you don't know the theory of these optimal binary search trees behind it. But I did want to put the code how to do it on the slide. I'm not sure if it's worthwhile going through the details of the code, really. A more graphical way to represent it is as here. Let's maybe take these first two runs as an example. So that was the first two runs that Powersort looked at. You take those two runs, and now you compute this blue interval, which starts from the midpoint of the first run and ends with the midpoint of the second run. So middle of this run, that's this blue little line. And now I start at the top. I go, this is my entire array. It has a midpoint at 1/2. So if left endpoint is 0, right endpoint is 1, 1/2 is in the middle. I can ask, is this point 1/2 contained in this blue interval? No, it's not. It's far to the right. So I have to continue to the next level. At this point, I divide it into quarters. Is any of the quarters inside my blue interval? Yes or no? No again. The smallest is still to the right, so I have to go one level down. Now I take eighths. And here I find that 1/8 is actually contained in this blue part. And so on the third level, I have one of these red ticks inside the blue interval. That's why the power is 3. And similarly for the others, if you pick any of the other blue ones, this one came out as 1 because the 1/2 point is contained in this. If you go to this last one, that's a very small one, so not even the third one was contained, but the 15/16 one was contained, so it gets a power of 4. I know this looks a bit mysterious why this is a good idea. And I don't want to go into the details, but there's a way to make this very intuitive. It just takes more time. This was the tree again that we followed with the merges. And so you notice you can put the root at 1. That splits the thing into the left and the right part. And then you pick the next one that's highest up, and you keep splitting like this. That's how you can get the tree. And there's another way to visualize this. If you put these blue bars, you put the highest in the middle, and then between the left boundary, right boundary, and middle, you put 2 bars of 1 height less. And then in each of the resulting segments, you put 1 bar more. So you put these 4 ones in. That gives you another way to see. So you could imagine having these light blue bars stack up, and then you let the dark blue intervals sink down, and they will stop whenever they hit the first of these poles. It's just another way to visualize the same thing. So let me wrap this up. Again, so I think the details of these last 2 slides, 35 and 36, they shouldn't pop up in the exam just because this is detailed stuff from my research. But is a lovely topic, so you're very welcome to dig into it. But yeah, it won't be on the exam, other than the abstract idea. What's good about Powersort is that it retains all the advantages of Timsort. You can take indeed the same code and just replace part of it. In particular, you still have this good locality of memory accesses. You don't need recursion. It's another thing that is nice in Timsort. You don't have to rely on the recursive call stack. You can, again, prove merge cost is, I've said this before, but it's a while ago. We have this lower bound h, and we have the +2n that you sometimes need, and you never need more in Powersort, same as for Peaksort. And finding the order to merge runs has minimal overhead. I didn't talk about the code here, but you can even replace this loop with bit tricks, so it's constant time even on word RAM magic. So it's very low overhead, and also very low overhead in practice.